In this video, we'll take a look at complex eigenvalues and eigenvectors. The problem is to find a basis for each eigenspace of the given matrix A. We should start by finding the eigenvalues of A. We'll take the determinant of A minus lambda I and set that equal to 0. To set up this determinant, we'll subtract lambda from the diagonal entries, and we'll leave the off-diagonal entries the same. We'll set that determinant there equal to 0. So the determinant gives us 9 minus lambda times 7 minus lambda, and then plus 5, and that's equal to 0. So expanding this product here, we've got 63 minus 9 lambda minus 7 lambda plus lambda squared plus 5 is equal to 0. In other words, our polynomial looks like lambda squared minus 16 lambda plus 68, and that is equal to 0. Using the quadratic formula, lambda is equal to positive 16 plus or minus the square root of negative 16 squared minus 4 times 1 times 68 all over 2 times our leading coefficient. So if we simplify this, lambda is equal to 16 plus or minus the square root of negative 16 all over 2. And let's take a closer look at this square root. We could re-express that root as root 16 times root negative 1. In other words, that root is 4 times I. So rewriting lambda, we've got 16 plus or minus 4i all over 2. Eigenvalues are 8 plus or minus 2i. Let's take a look at the eigenspace associated with the eigenvalue 8 plus 2i. So to do that, we're going to set up the system A minus lambda I, where our lambda is 8 plus 2i. And this is a homogeneous system. So what we're going to be doing is subtracting 8 plus 2i from the diagonal entries. We'll have to be really careful of the signs here to make sure that this 2i is being subtracted off. So the diagonal entries are going to look like 1 minus 2i and negative 1 minus 2i. The off-diagonal entries won't be changing. Now we'd like to get this matrix into our REF. Probably best to swap rows here. We'll swap rows 1 and row 2. And that way we can divide the top row by 5 and create a 1 in the upper left-hand corner. Let's take row 2 minus 1 minus 2i times our pivot row. So top row will not be changing. And in the bottom row, we've got 0. An entry here that will require a little bit of extra attention. And over on the right side, we'll have a 0. So let's work out this entry in the bottom right here. We would have negative 1 minus 1 minus 2i times this entry right here. So minus 1 minus 2i over 5. So I think I'll leave the negative 1 out in front, and I'm going to distribute this negative sign here through the second bracket because that's going to decrease the number of negative signs that we have to deal with. So I'm going to write plus 1 minus 2i times, now everything in the second bracket is going to become positive. We got 1 plus 2i over 5. So that gives us negative 1 plus, we're going to have an expression all over 5. And as we multiply out the numerators, we've got 1 plus 2i minus 2i. Those cancel, so I'm not going to write those down. And then we'll have a minus 4i squared, which is the same thing as positive 4. So there we go. We've got negative 1 plus 1 equals 0. And there we have our RREF for this matrix. To find our eigenvectors, let's name our variables x1 and x2. And let's notice that we've got a leading one in the first row, but we do not have a leading one in that second column. So that second column, x2, is going to get a parameter. Let's say x2 is t. And the top row tells us that x1 minus 1 minus 2i over 5 times x2 is equal to 0. In other words, x1 is equal to positive 1 plus 2i over 5 times x2. In other words, x1 is equal to 1 plus 2i over 5 times t. So that tells us that our eigenvectors x have the following form. I'm going to bring the factor of t outside. First component looks like 1 plus 2i over 5 times t. Second component looks like 1 times t. So in terms of choosing a basis for this eigenspace here, we could say a basis is the vector 1 plus 2i over 5 and then 1. Or if we prefer to clean this up a little bit, we could multiply both components through by 5 just to eliminate the fraction. So a nicer choice of basis vector would be 1 plus 2i, 5. So at this point we've found our eigenvalues and we've investigated one of our eigenspaces. We now need to look at the other eigenspace corresponding to the eigenvalue 8 minus 2i. So to look at that, we're going to build the system a minus lambda I. We'll be careful with our brackets here to make sure that our eigenvalue is fully subtracted off the diagonal entries, and this is a homogeneous system. So looking at these diagonal entries, it's as if we're subtracting 8 and adding 2i to those diagonal entries. The diagonal entries will be 1 plus 2i and negative 1 plus 2i. The off-diagonal entries will stay the same. We've got zeros on the right side. So let's swap these two rows. Now let's divide row 1 by 5. Next, we need to take row 2 and subtract off 1 plus 2i times our pivot row. That will give us 0, something, and 0 in the bottom row. So let's look at this something here. This entry is going to be negative 1 minus 1 plus 2i times negative 1 plus 2i over 5. So let's take this negative sign here and distribute it with the second bracket here just to make the calculation go a little bit easier. So I'm going to write plus 1 plus 2i, and these terms in the second bracket are going to change sign. It'll be 1 minus 2i over 5. That way we've got negative 1 plus something over 5, and in the numerator we've got 1, we've got minus 2i and plus 2i. Since those cancel, I'm not going to write those down. And we've got minus 4i squared, which gives us plus 4. So this entry here works out to 0. And there we have our RREF. Let's name our variables x1 and x2. We've got a leading one in the first row, but there's no leading one in the second row. So that leaves us a column here without a leading entry. That tells us that x2 takes on a parameter. x2 is t. The top row says that x1 minus 1 plus 2i over 5 times x2 equals 0. If we bring that second term over to the other side, the signs are going to change. So x1 is equal to positive 1 minus 2i over 5 times x2. In other words, x1 is equal to 1 minus 2i over 5 times t. So the eigenvectors that we're getting have the following form. I'm going to factor out the t, and the vectors are going to look like 1 minus 2i over 5 and then 1. So any non-zero multiple of this vector here is going to be an eigenvector corresponding to this particular eigenvalue. In terms of writing down our basis for this particular eigenspace, we could say a basis is 1 minus 2i over 5 and then 1. That is a basis vector. But a little bit nicer here to multiply those components through by 5 just to eliminate the fractions. A nicer basis vector would be 1 minus 2i and then 5. So let's summarize the problem here. We were asked to find a basis for each eigenspace of A. We first figured out our eigenvalues. There were 2 of them. We then investigated the eigenspace for the first eigenvalue there. We found a basis for that. And we have just now found a basis for our second eigenspace. So let's label this clearly. And there we have our final answer.